now it's not allowed for anymore. But still, now I have to buy new ones.
That's why I never go into the locker room.
No, it wasn't the locker room.
No, I know, but somebody's going like room.
Oh, really?
Yeah. Well, put the candy in my bag, I don't care. Charger.
But you're not really answering the third question.
Oh, I just
I say you're not really answering the third part of the question.
That's the fun one it was.
Okay, Monday evening I spent before the passage of yesterday, before the evening, we had police on your going through the yards, looking in the it all started for me
That drug thing.
being called shelter in place road.
Yeah, my date started yesterday, right when I woke up and checked my ECT. No. No, it was, okay, it was fine. Like, if I say, it would be like, oh, that was fine. But today? Oh, yes, to make the day even better.
No, okay. Let's just say, work, after school, pretty little. Any other day, any other time.
Last time I did better than that. Okay, so 2 tests ago, I got 6. Last time. Yeah, that's good. Yeah. Last semester, I found I got like a 32 already.
You get lower.
I got 20.
So if you're doing something like
No, I'm taking it.
you are?
I'm taking it.
Yeah, how many?
No,
How
I
many
just
times
want
are
to
you
get
allowed?
as many times as you want. It sucks. They have a eating office, I guess. She's just taking it. She's like an eating office.
Okay, so I would probably accept Henry's law being stated the way I gave it to you for working purposes. You know, solubility over pressure, solubility over pressure. Technically, we use lowercase c for solubility. I didn't because of confusing you all more. Capital S really is entropy, and we'll be getting into that. But I kind of use a little teaching discretion there. So, solubility is proportional to pressure. Really would be stated this way, technically speaking, and I can tell who's read the book. So C is proportional to P. We don't like proportionality, so to change it to an equality, we have to put in a constant. So this is a technical statement. Just like Charles' law, volume is proportional to temperature. So the constant equals this, and if it's constant for any given pressure, these have to equal the same number, so you end up with a thing that looks like this. So basically, I cut to the chase here for this. Okay. So, see solubility, P is pressure, and K is your constant at that temperature, whatever temperature you're working at. Now, as far as explain the law in terms of kinetic molecular theory of gases. In order to get something to dissolve, you have to have collisions between the solute and the solvent. Remember I talked about all that stuff? Okay. So what would increase the number of collisions in regards to this? Well, the more pressure you push downward on the gas, isn't it like squeezing it towards the surface of the liquid? So you're gonna have the gas particles hitting the particles of the liquid more, therefore giving it more of a chance to form those associations and solvents, increasing solubility. So that's what it means by using kinetic molecular theory of gases. Kinetic molecular, you know, the kinetic energy of molecules. How are they moving? How does that factor in? I find I need to give you a lot of advice on how to interpret what's being asked in the question, if you follow what I'm saying. And I'm hoping it's catching on a little bit. That was 29, right?
Yep.
So 31. A student is observing two pieces of water. Well, the teacher's laughing a smart one. I mean, one beaker is heated to 30 degrees Celsius and the other is heated to 100 degrees Celsius. In each case, bubbles are forming in the water. Are these bubbles of the same origin? Explain.
Oh, I think I got it. Yeah.
And 100 degrees, it's 1.9.
Like 100 and 490, it's just there. It's just hot.
Yeah, I just said because extra bubbles are trapped in the water.
This will tell me if you're really thinking things through. This is one of those like combination jumps where you have to get over the first one, take a straw out, and then jump over.
I didn't think it was a combination. I thought it was a regular one.
So I hope you have your helmets on, buckle it up,
That would be
your heels down.
I'm ready. I was so bad on the horse. Yeah.
But you're not telling me, you're not giving me a question. Don't be lazy.
Oh, I know it.
You said report right at the end with an incomplete explanation. Okay, but your explanation isn't really hitting it on the head. It's the words involved.
Let's see if we fell or if we cleared. We probably like thought we were wanting one.
Same thing I said to the dude in the back.
We thought we were gonna be good, but then the horse just kept going. Don't erase the whole thing.
Vapor pressure.
Okay, so some of you crashed, some of you
We
made
cleared
it over the
those
first
off.
fence, but you nicked the second fence, and some of you made it over both.
We made it over one,
Combination.
and then the horse kept going.
I wouldn't say I ever say I've called the ambulance, then you know that.
Then we're good.
Okay, so at 30 degrees, you are not at the boiling point, but you are heating the water, right? The solubility of gases in liquids decreases with increasing temperature. So as you heat it up, there's always some air dissolved in the water. As you heat it up, you're decreasing the solubility of the air in water. So what's really coming out in those bubbles, for the most part, is the air that can no longer be dissolved in the water. Yes, you do have a little bit of water vapor there because of the phase change probably happening, but the main thing is here. Once you hit 100, you can have the phase change occurring beneath the surface. Up until then, it's happening at the surface, so the water vapor is just kind of coming off the surface for the most part. Once you hit 100, you have boiling, so the bubbles that are actually coming up and popping are water vapor with a little bit of air. So it's kind of like, first at 30, it's a lot of air, a little bit of water vapor. Then at 100, it's a lot of water vapor, a little bit